In this chapter, guys, we're going to be talking about just linear functions. And if you guys remember correctly, a linear function is a function that when you plot the points, given your x and y's, and you connect them, that you're going to have a line. And one of the things that is critical in understanding a linear function is the angle at which the graph goes up and down. And so when we talk about that, that's going to be called slope. And that's related to rate of change. So we're going to talk about how those two things are related, and then we're going to get into some more details about how this is useful. But I thought we would look at the solve it problem to start, the get it ready problem. And here we go. So the table on the right here says that is a horizontal and vertical distances from the base of the mountain at several poles along the path of the ski lift. The poles are connected by a cable. Between which two poles is the cable's path steepest? And how do you know? So again, this, if you can imagine being at the ski area, and between each of the lift towers, the cable kind of connects at each one of those towers. And based on the information here in the graph or in the chart, we want to figure out between which two poles it's the steepest. And we can look at this, and we can see that the common differences between the horizontal distance, so the distance if you're measuring from across to each one, right, is 20 between the first two, 20 between the second two, and it goes up at 40 from the second two, or between the third and the fourth. But that's not really important right now, because we'll see in a second we can handle that. So it says when the horizontal distance between the two pairs of poles is the same, how can you use the vertical distance to determine which pair of poles the cable is steepest? Well, you can probably figure this out, right? If it's the same amount of distance between each one, if one is much higher than the other one, the line's going to have to be much steeper there, right? So when the change in the horizontal distance between the poles is the same, compare the vertical changes. So these are the side to side, right? So if you were going to just walk the distance on a straight line, and these are the up and down distance between the poles. And what we're showing you here is that from pole A to pole B went up by 5, and then from pole B to pole C it went up 25. And then from C to D it went up 10. And that doesn't matter. It's still it's not as big as 25, and it went up 40. So at this point, it'd be the distance between these 2 points, which is the biggest difference. Okay? All right, so we're going to talk a little bit more about how we use this in the next part of this.
In this problem, you will find a rate of change using a table. The table shows the distance a band marches over time. Is the rate of change in distance with respect to the time constant? What does the rate of change represent?
So we're looking at a chart that's similar here, and the good news is they are going up by ones here, so you don't have to worry about too much here. It's just this is the section we're going to really need to focus on and consider.
The rate of change is equal to the change in the dependent variable divided by the change in the independent variable. Which is the dependent variable?
Well, if you guys remember correctly, we've been talking about this. It tends to be, well, not tend to be, it is the x value sort of in your table that is your independent variable, and it's the y values that are dependent, right? So
since the distance the marching band travels depends on how long the band has been marching, the distance is the dependent variable. The rate of change is the change in distance divided by the change in time.
So these are sort of like our x values, these are our y values, and it makes sense, right? Because how far they march depends on these numbers over here. Okay, and the rate of change is this: we're going to divide the difference between these numbers by the difference between these two numbers.
Does this problem look like one you've seen before? Yes. In Lesson 2-6, you wrote rates and unit rates. The rate of change in this problem is an example of a unit rate.
When we did unit rates, we talked about stuff like miles per hour, feet per second, that kind of thing. So really, it's just the comparison between the differences of these y values divided by these down to just having 1 in the denominator. Wanting to know how far in 1 minute or how far in 1 mile, or how far in 1 second.
Calculate the rate of change from one row of the table to the next. First, find the rate of change for the first 2 rows in the table.
So we took the values in the y over here and said, what's the difference between 520 and 260? And the difference between 520 and 260 is 260. And we want to know the difference between the x values, 2 and 1, so that's 1. And what we're going to try to do now is figure out if it's going to go up the same in each one of these. And if it is, then we'll know that we have a constant rate of change.
Then, compare the next 2 rows.
So we're going to subtract the difference between these two, the difference between those two, and we should get 260 as well. And the difference between the x values is also 1. So far, so good. So we have a constant change in the y's and a constant change in the x's. Again, it's always important to know that we're going to put the change in the y's on top of the changes in the x's. So the change in the range goes over the change in the domain.
Finally, compare the last 2 rows. Since the rate is the same between each pair of rows in the table, the rate of change is constant at 260 feet per minute. The rate of change represents the distance the band marches per minute.
So this is, I mean, it may look a little complicated, but really all you're doing is seeing it goes from add 260 to 260, 520. Add 260 to 520, you get 780. Add 260 to 780, you get 1040. And so if they're all going up the same, and these are all going up the same as well, and when you divide them, you get the same unit rate, or the same, when you put 1 in the denominator and you make sure you only have one, the same. When we have only 1 in the bottom, and then we know it on the top, and it goes the same for each one, we know that we have a constant rate of change.
Now it's your turn.
So this one is essentially, it's the same problem. They're just saying that in problem 1, you calculate the rate of change in distance respect to time using consecutive rows in this table. Can you get the same rate of change if you use non-consecutive rows? Well, yeah, you can. So and here's how it works. Because if you go up from, they're showing you from 260 to 780, right? The distance is 520. But because you went from row 1 to row 3, or from time 1 to time 3, you went up 2 in this case. So when you divide that 520 by 2, you get 260. And I mean, if you jump 2 here, you'd have to jump 2 on these. So if you were comparing values based upon that, you'd have to be skipping by the same amount each time. I'll explain this some more in class once we do some examples. But that's really, we're gonna work off of this for this whole section. And I mean, if you can grasp this, it should not. The rest of this chapter should be pretty darn easy. Okay, so we'll stop here.